This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Today's discussion centers on a research paper detailing a novel prognostic framework for deep space habitats. The authors tackle the complex challenge of predicting remaining useful life RUL in systems with multiple, unlabeled failure modes. What are the key limitations of existing prognostics methods that this paper addresses?
Existing methods often struggle with the high dimensionality and complexity of sensor data from deep space habitats. Many sensors might be redundant or only relevant to specific failure modes, which are often unknown. Furthermore, traditional approaches frequently rely on labeled data, which is scarce and expensive to obtain in the context of deep space missions. This paper directly addresses the lack of labeled data and the need for efficient sensor fusion techniques in the presence of multiple unknown failure modes.
The paper proposes a two-phase framework: offline sensor selection and online diagnosis and prognostics. Let's start with the offline phase. Can you elaborate on the methodology used for sensor selection, given the absence of failure mode labels?
The offline phase leverages a mixture of Gaussian regressions, MGR, to model the relationship between sensor data and time to failure. A novel expectation maximization (EM) algorithm is employed to simultaneously cluster degradation trajectories, effectively assigning unlabeled failure modes, and select informative sensors for each identified mode. This is achieved by incorporating an adaptive sparse group lasso penalty into the EM algorithm's M step, allowing for simultaneous parameter estimation and sensor selection.
The use of an EM algorithm is interesting. How does this algorithm handle the uncertainty inherent in the unlabeled data and the mode-specific sensor relevance?
The EM algorithm iteratively refines estimates of the model parameters, including failure mode probabilities and sensor weights, and the latent failure mode assignments. The E-step calculates the probability of each data point belonging to each failure mode given the current parameter estimates. The M-step then updates the parameters to maximize the expected complete data log likelihood, incorporating the adaptive sparse group lasso penalty to perform sensor selection. This iterative process converges to a local optimum, providing both failure mode assignments and a mode-specific sensor subset.
The adaptive sparse group lasso penalty is crucial here. Can you explain its role in the sensor selection process?
The adaptive sparse group lasso penalty encourages sparsity at both the individual sensor level and the group level, representing features from each sensor. The group lasso penalty shrinks the coefficients of entire sensor groups towards zero, effectively selecting or deselecting sensors. The individual lasso penalty further refines the selection by shrinking individual coefficients within selected sensor groups, improving prediction accuracy. The adaptive aspect adjusts the penalty based on initial coefficient estimates, making the selection process more robust.
Moving to the online phase, how does the system diagnose the active failure mode and predict RUL in real time?
In the online phase, multivariate functional principal component analysis, MFPCA, is used to extract low-dimensional features from the selected sensors. A K-Newest neighbor, KNN classifier, trained on the offline phase's results, diagnoses the active failure mode based on these features. Finally, a weighted functional regression model, specific to the diagnosed failure mode, predicts the RUL using the MFPC scores. The weighting scheme accounts for potential outliers identified during the offline phase.
The paper mentions two case studies, a simulated dataset and the NASA turbofan engine dataset. What were the key findings from these evaluations?
The simulated dataset allowed for a controlled evaluation of the methodology's ability to handle various signal-to-noise ratios and different levels of sensor informativeness. The results demonstrated good performance in failure mode clustering, sensor selection, and RUL prediction, even under noisy conditions. The NASA turbofan engine dataset provided a more realistic testbed, showcasing the method's effectiveness in a real-world scenario with partially observed degradation and unlabeled failure modes. The proposed method outperformed baseline approaches, particularly in early life RUL prediction.
What are the key limitations of the proposed methodology, and what avenues for future research do the authors suggest?
A key limitation is the assumption of a linear relationship between the log of time to failure and the sensor signals. The authors suggest exploring nonlinear models to improve accuracy and capture more complex degradation patterns. Another area for future work is extending the methodology to handle scenarios with more complex dependencies between failure modes or situations where the number of failure modes is unknown.
The paper highlights the importance of unsupervised learning in prognostics for deep space applications. How significant is this contribution, considering the challenges of data scarcity and labeling in such environments?
The contribution is significant because it directly addresses the practical limitations of obtaining labeled data in deep space missions. By developing an unsupervised framework, the authors provide a more realistic and scalable solution for RUR prediction in these challenging environments. The ability to simultaneously cluster failure modes and select informative sensors is a key advancement, improving both the accuracy and interpretability of the prognostics model.
The use of functional data analysis techniques like FPCA and MFPCA is prominent in this work. What advantages do these techniques offer in this specific application?
Functional data analysis techniques are well suited for handling the time series nature of sensor data. FPCA and MFPCA effectively reduce the dimensionality of the data while preserving important temporal information. This dimensionality reduction is crucial for managing the high-dimensional sensor data from deep space habitats and improving the efficiency and robustness of the subsequent regression models. The ability to handle time-varying signals is also a key advantage.
The paper emphasizes the importance of interpretability. How does the proposed methodology contribute to a more interpretable prognostics model?
The interpretability stems from several aspects of the methodology. First, the sensor selection process explicitly identifies the sensors most relevant to each failure mode, providing insights into the underlying degradation mechanisms. Second, the clustering of degradation trajectories provides a way to categorize and understand different failure modes. Finally, the use of relatively simple regression models after dimensionality reduction makes the model easier to understand and interpret compared to more complex black box approaches.
The adaptive nature of the sparse group lasso penalty is a key feature. How does this adaptivity improve the robustness of the sensor selection process?
The adaptivity comes from weighting the penalty terms based on initial coefficient estimates. This means that sensors with initially larger coefficients, indicating stronger relevance, are penalized less, while sensors with initially smaller coefficients are penalized more. This prevents strong signals from dominating the selection process and makes the selection more robust to noise and outliers. It's a form of reweighting that improves the overall performance and stability of the algorithm.
The paper mentions the use of a weighted functional regression model in the online phase. Why is weighting necessary, and how does it improve the accuracy of RUL prediction?
Weighting is crucial to account for potential outliers or misclassified samples in the training data. By assigning lower weights to outliers, the influence of these erroneous data points on the regression model is reduced, leading to more robust and accurate RUL predictions. The weights are determined based on the distance of each data point from the centroid of its assigned failure mode cluster.
In summary, this paper presents a comprehensive and innovative approach to prognostics for deep space habitats. The combination of unsupervised learning, adaptive regularization, and functional data analysis techniques offers a powerful framework for addressing the challenges of high-dimensional, unlabeled data and mode-specific sensor relevance. Thank you.